Hello everyone, welcome back. Today we're going to talking about the Lab 4 of 16 bits ALU design. So let's go to our website and in our web page this time. So here is the ISE projects we created before. So let's download this ISE folder and open the PDF file. Here is the documents you have. So this week we go back to the ISE design. So use the HDL code. So it's totally different with the assembly code. So I hope during the Lab 3 you have already know about the MIPS assembly language. So after you download the zip file, it's ALU 16 bits. Open the folder and you can see the project for ISE project. So double click, open this project. After open it, here is the system. On the left, the hierarchy window, you can see the hierarchy for the 16-bit ALU. We will use the 1-bit ALU and then compose the 16-bit ALU. So first, let's design ALU 1-bit. So double click, so you can open the ALU. Here is the 1-bit ALU. And you can see here, I gave you the ports definition for the entity, and for each component you might be used later. And the behavior of this module is empty, so you have to fill in the blanks. So I just give you a quick demo for here how to design it. So on your PDF file, go to the page 3. On the bottom of page 3, you can see here is the structure, a schematic diagram for the 1-bit ALU. In the 1-bit ALU, there are 3 components. For the full adder, AND gate, OR gate, and then there's another component is called MUX31. So MUX31 is multiplexing. There are 3 inputs for this MUX, and there's 1 output. And the output is based on the selection signal it's given from outside, is S here. So which means that you give the value to S, and the MUX31 has different output to choose from the full adder or the AND gate or the OR gate. So there's 3 choose 1. Okay. The full adder is exactly what we learned before, and if you forgot how to design it, you can just a quick review or go to the video recap. So yeah, let's just follow this diagram and to design the first full adder part. Full adder logic I already gave you. So here is just use the instantiate this. If you forget, just go through the video recap before. Okay. So according to the diagram, so the logic, the A port for the full adder actually is A, and the B is a little difficult, so it's just leave it for a second. C in is the C in port, and the S out is the signal connect to the MUX. So here's is a line. So as I said, if there are 2 modules and they connect to the by a line, we name it signal. So you have to declare the signal. Here I name it S out for adder. So indicate this is the S out for adder port. And S out is the the C out is the C out. So okay, so right now the port B is a difficult. Port B is because the full adder have to dealing with the subtraction. So we use the 2-bits complement to do the subtraction. So if you like, you can just read this part, and we have to use the XOR gate to cooperate. So let's go back to here. So actually, before we use the signal B, we have to use the B XOR the selection signal in the 0-bit. The 0-bit of selection signal, and I give it to the NB. So then the NB is actually the NB is the new signal goes into the B port. So after we declare this, so we have to declare the signals. We have the NB. So NB is a new signal. And then we have another signal, it's called SOut for adder. Okay, so far so good. So we designed the first part. So for this case, so you design the first part for the ALU, the full adder part. Okay, so let me just quickly show you this. So for the full adder, and the port A is the A port, and the B is the output from the XOR gate. So here we can use the XOR. And this line is called NB. And here this is the SL, so this is C in. Okay, this line is C in, and here this output is S out for adder, so it goes to the mux. And then you can choose the property one, and just like how we create the 4 bits, the full adder, and you can know how to design it based on this structure. So based on the structure, we have the still the AND gate, OR gate, and the mux 3 1. So think about it and fill in the blank. So after you design the ALU, finish this part, so the 1-bit ALU is ready to use. And then we can go to double click to the 16-bit ALU. Here is the top module for the 16-bit ALU. So in the PDF file, go down to the next page. This page, the diagram will show you how to connect the multiple 1-bit ALU to compose a 16-bit ALU. So there's a name for each one. So right now the input A is 16 bits and input B is 16 bits. So and the C out from one bit ALU goes to the next ALU C in port. So exactly the same with the 4 bits for adder. And here I gave you the old instantiate, and the port map here is the empty premises. And I want to show you is when we define the port map, this is the one way we define it. We list all the ports of this component and give the proper signal or ports on the right. The other way we can do is we can hide the ports of this module and just give the connection here. So for example, for here the ALU, I know the ports order, the first one is A, second one is B, and then is selection signal. The C in as selection signal and S out and the carry. So we can just directly give the connection to that here. Yeah, let me show you. Okay, so the first one, the first input is the 0 bit of A, and the second one is B, also is B0. And then the C in is S0, selection S. So don't forget the premises here. Okay. So although on the diagram there's just give you S0, but which means the 0 bit of S. And the S out is S out 0 bit. Okay, and the C out. Oh, sorry, I forgot. This here is S. This port is S. And here is S out. S out is used to align, combine them together, so there's a signal. And I already defined a signal. It's called carry. It's called carry. So we can just directly write the carry here. The carry 0. It's a 0 bits. So the carry here. So this is how we connect this. We can declare the port map like this way. Okay. So you know, follow the diagram. You know how to do the next one for the next one. Okay. But pay attention to the last one. For the last one, you can get the point. So the last one is A15, and then B15, and S. Sorry, this time the C in is from the previous one. The C in is carry 14 from the previous ALU 14, and the S, and this time S out is 15 bits. Sorry, my timer. The last one is not a carry 15 because we only have. So the last one is not the carry 15. Is actually that is the C out for this old module, for the ALU's module. So pay attention to the last one. Okay, and I know you can figure out the middle one. Okay. So we'll finish this, and it's almost there. So last step is to create the test bench. So the test bench is already here. It's just double click to open it, and it goes to here to the bottom. Here the stimulus. I give you an example for the first one. How to test what kind of test bench you want to test. In the PDF file, here's a table, and this table is showing you what kind of value you need to test. So it gives you the S1, S0's value, 0001. Okay, follow this one, follow these operations, and to test the results. The first one is 100 and the 230, and they give you the example here. So this one is 100, and the second one is 230, and this is the add. So S here, this is S1, this bit is S1, this bit is S0, is 00. And according to the PDF file, we know this is doing the add. And you can just easily to copy that part to copy these 3 lines and change these values. And you can use the calculator in the Windows to help you to calculate the value. Just change it to the programmer and click the word. The width is word. And for example, if I need a value, for example, 500, so I can just type 500 and change the type to the hexadecimal. You know this value is 1F4. And we have 16 bits for each input, so in the test bench, you just enter 0, 1, F4. The same thing for the negative number. For example, negative 20. Change back to the decimal, and you can just press 20, and here is the sign. Here is negative 20, and change it to the hexadecimal. You see the negative 20 is FFEC, so you can just write this value into in your test bench. Okay, that's how to create a test bench, and after you finish all of them, let me show you the final results. So change the design from the implementation to the simulation, and click the test bench. Don't forget to click on the test bench and then click the simulate behavioral model. Double click and it's running. And for this case, our simulation is longer than before, so we have to change the time. On default, the simulation will run 1 milliseconds. Let's change it to the 1.2 and click the restart, and then click here the run again. Okay, and change the A, B, and S out the regex to signed decimal number, and click here. So this is auto change the view. Okay. Okay, here is the results. Okay. If you like, you can change the signal and make it easy to read. Okay, easier to read. Okay. So 00 is add, it's addition. So 100 plus 230 is this value, and this is the minus. 55 minus 70. Oh, yes, negative 15. So, and here is logic AND and the logic OR. So give me a screenshot for this one for your final results, and then fill in the blanks in the table, for this table, and put the table and screenshot in your lab reports, and that is the lab 4. So if you have a question, let me know, okay, through the email or ask me the question during the lab session. So this is the lab 4. Thank you for your time. I'll see you next time.